This video lecture is about the nature and origin of the universe and how it changes over time.
The lecture outline starts off with what might seem like a silly question. Why is the night sky dark? Hear me out for just a minute so I can explain why the answer is not because the sun went down. Since the universe has stuff in it, there is mass, which means there's gravity. If the universe is ageless and static, it must be infinite in size, or it would have collapsed long ago. But if the universe is ageless, static, and infinite in size, the night sky should be as bright as the sun. That's because no matter what direction you look, your line of sight will eventually run into a bright object. Yes, farther away objects are fainter, but there are also more of them, so each shell of greater distance has the same overall brightness. Recall from the galaxies lecture that the universe is not static. It is expanding. Visible light from all those distant bright sources is redshifted to longer wavelengths. So you can get a dark sky, but it would be bright in the radio band. The Hubble-Lemaitre expansion is an expansion of the space between galaxies, so the light is stretched out as it travels from other galaxies to us. The whole coordinate grid system is expanding to make a cosmological redshift. The galaxies are not moving through space that is already there. We now know that the universe had a beginning. All of the galaxies were very close together long ago. When we looked at the changing number of active galaxies with increasing distance, we saw that the number of them increases at great distances and then falls off dramatically at very great distances, which tells us about a time before the galaxies had formed. What that means is that there is a time horizon beyond which the light from very distant objects has not had enough time to reach us yet. The Hubble-Lemaitre law of the universe's expansion says that the speed of a receding galaxy equals the Hubble constant, h, times the distance of the galaxy. That means that 1 over h is equal to the distance divided by speed, which is equal to the time it took for the galaxies to get to where they are. The age of the universe is going to look like 1 over h. The Hubble constant tells us the expansion rate of the universe. If the Hubble constant h is large, that is, if the expansion rate is large, the derived age of the universe is small because it did not take the galaxies long to get to where they are now. Next slide. Einstein's theory of general relativity says that gravity is a warping of space-time. On the scale of the universe, the whole universe space-time is curved, and the whole coordinate system is expanding. To try to picture how our three-dimensional space is curved, let's use the analogy of a two-dimensional surface curving into a third dimension. Our up-down dimension collapsed down to nothing. So in flatland, there is no experience of our up or down. Despite that limitation, how could you determine that your two-dimensional universe was curved? If the surface curves back on itself like a sphere, then someone traveling in the same direction will eventually come back to the starting point. This universe has a finite size but no edge. We know that on a flat surface, the angles of a triangle add up to 180 degrees. In a spherically curved universe, the angles of really large triangles add up to more than 180 degrees. Consider that at the equator of the Earth, the lines of longitude running north-south intercept the equator at a 90-degree angle and converge at the poles. So a triangle made up of one point on the equator plus the North Pole plus another point on the equator will have the angles add up to much more than 180 degrees. A spherically curved universe has a positive curvature. On sufficiently small scales, the surface looks flat, so the regular geometry rules apply. The angles in a small triangle add up to 180 degrees. Here on the surface of the Earth looks flat to us because the curvature of the Earth is so much larger than we are. The universe does not have to curve back on itself. Instead of a positive curvature, the universe could have a negative curvature, curving away from itself. A two-dimensional analogy would look like a saddle. The angles in large triangles would add up to less than 180 degrees. Like the positively curved universe, there would be no center on the surface and no edge. Rather than setting up big triangles in the universe, astronomers can use how the number of galaxies increases with increasing distance. If the universe has zero curvature and the galaxies are spread roughly uniformly in the universe, then the number of galaxies should increase linearly with ever greater volume. Lines defining an angle spread out in straight lines. If the universe has positive curvature, then the number of galaxies increases with greater volume, then decreases with very large volumes. Lines defining an angle spread out at first and then converge at very great distances. If the universe has negative curvature, then the number of galaxies increases more rapidly with ever greater volume than a flat universe. Lines defining an angle diverge at increasing angles as the lines curve away from each other. In a universe like ours, the curvature is very small, so we would need to look to very large distances, and that's hard to do since distant objects are faint and difficult to measure accurately. We might have better luck with looking at how the brightness of objects with standardized luminosity changes with greater distance, such as type 1 supernovae. If the universe has positive curvature, the very distant objects will appear brighter than if the universe is flat. In the expanding universe, everyone seems to be at the center because everybody is moving away from everyone else. In this analogy, it looks like flatland is expanding into something beyond, but every analogy has its limits. In our 3D universe, space-time itself is expanding. Our universe is not expanding into anything beyond.